Now, B part 1 manifold. Okay, they belong to the intrinsic geometry exterior algebra in 3D. Now, today is April 1st. Okay? Now, in this lecture, lecture 5, we will develop just to get the basis at a point P belonging to the manifold M. Okay? I would say here a particular M is M3. Now, from the previous lecture 4, the tangent space, okay, put 3 over here, consists of all linear combination of the tangent vector V1 and V2. See, TPM, okay, they span by these two vectors over here. So it provides a linearized approximation of the manifold Fp, which is crucial in differential geometry for defined concepts such as differentiation, integration, and curvature. That's important here. Now, understand the local coordinates, okay? Now clear. A manifold is a collection of points, each one is labeled by coordinates C1, C2, and C3. If you are working then 4 dimension, okay, this will be 4 coordinates, okay? Now, the key point of this is first, coordinates are just labeled. Attention now, you see? Go back to lectures before, okay? In this part B, you see, are just labeled assigned to each point. Are labels, okay? I pointed out before that you just have a point, okay? You cannot do anything when you have a neighbor point to it, okay? There is no vector linking these 2 points, for instance. Now, to define a derivative, we need the notion of change, okay? To find the derivative, do you remember from calculus? See, you have x0, then the next point is next 0 plus delta x. See? Here, the concept of derivative in this manner does not happen. See, that's important here. So, how do derivative arise in the context of manifold? You see? Now, in this case, we present, okay, in this case, see, the tangent vector space here. But this, on the previous lectures, you see, CB part 1, lecture 2A and 2B, we already talked about this basis vector, okay? Clearly, we derived this. This is a vector space, and the basis for the tangent vector space are, you see, partial C1, C2, C3, in 3 dimensions, okay? So if you extend to higher dimension, this will just extend this basis vector here. Now, the base for cotangent vector space is dx. I'm sorry, this is C, okay? This is C here. C1, C2, C3. You see that a dual space, dual vector space. Okay? Now, you can relate the vector at the point P just with a curve. Remember the previous videos, okay? We derived this clearly, you see? Now the vector here, this is ordinary derivative of gamma I respect to lambda. At lambda is equal 0, lambda is equal 0, it is the point P with the intersection, okay, of the tangent plane with the manifold. Okay? P belongs to the manifold and to the tangent vector, as you pointed out before, okay, emphasized this before. Now, where those here are the components of the tangent vector in the coordinate system. Okay? Now here is Euclidean now. Okay? You approximate points around the point P belong to the manifold. We approximate to the tangent plane. See? That's approximation. So the tangent vector coordinate system. So this is the basis, okay, for the tangent space, okay, and also recall from lecture 2A and 2B that this inner product is delta ij. You see, I here is covariant. dxj is the contravariant basis. Okay. Now this is again. This is C. You see clearly. Okay. Now this is for you just to remark, to emphasize. You see, you have a region over here. Okay, at the manifold. This is a tangent plane. We approximate points around the point P, okay? In a manifold, we approximate to the tangent, okay? Like for instance, I will show here, okay? So, I have a manifold here. You have a point here. I have a tangent plane. There is a point here around this point P, which approximate to this tangent plane here, okay? Because P coincides with the tangent and with the manifold. The set of this point here we call chart. The next video will show how to construct a chart, okay, around a certain point P. That's a subject for the next lecture, a chart. You see how to construct a chart. Okay, the approximate point in the small region of the manifold. We approximate points that we call chart.